Hello, everyone. This is Zinke with Zinke's Math Academy. Today, we'll talk about an AMC 12 problem from the fall 2021 AMC 12A. I'm running on maybe 4 hours of sleep, so hopefully my voice can keep up. Yeah, so here's the problem. It says a convex quadrilateral ABCD has AB equals 18. Angle A is 60 degrees and AB is parallel to CD, so it's a trapezoid. In some order, the lengths of the sides form an arithmetic progression, and AB is the side of maximum length. Length of another side is A. What is the sum of all possible values of A? So we might as well start off drawing a diagram. Could look something like this. Could look something like this. Don't really know for sure yet, but probably look like one of these two rough shapes of trapezoids. And these are the parallel sides. So let's see. It says the sides are in arithmetic progression, but it doesn't say what order. So let's just try a random order and see how it goes. So before I really start, let me just say we'll explore this problem. We'll think about how we can do it faster, and then I'll give some final remarks on the problem. So let's just say this is 18, 18 minus x, 18 minus 2x, and so on. So, it seems a little bit hard because, how do we deal with all the three unknown sides, right? All we're given is one max side, which is of maximum length, and an angle adjacent to that side. So one pretty common trick that can help with these trapezoid problems where you're given all four side lengths and two parallel sides is you can quote unquote remove a parallelogram to make it a triangle problem. So what do I mean by removing a parallelogram? Well, if we look here, let's just remove this parallelogram. So I'll draw a new diagram. So if we remove this red parallelogram, let's see what happens, right? So the sides were 18 minus 2x. So this opposite side of the red parallelogram is also 18 minus 2x. This is 18 minus 3x. So this is also 18 minus 3x. And then the bottom was a total length of 18. So this part is just, 2x. And then this is still the same, 18 minus x. So what we see here is, after removing the red parallelogram, we get this green triangle. And the nice thing about the green triangle is, it still has the angle of 60. So we can use law of cosines to relate the three sides lengths. So let me just mark that the red thing is in fact a parallelogram by my construction. So now let's see what happens if we try law of cosines on this, right? Because why not? This is probably quickest thing. So if we use law of cosines on the 60-degree angle at A, we'll get something like the adjacent side square plus the other adjacent side square to the 60-degree angle minus 2 maybe cosine of the angle in between equals the third side squared. So if we expand this all out, let's make that 9. So 54, 108 equals, let's see, this will be 4x squared plus x squared minus. So the cosine 60, that's 1/2. It'll cancel out with the 2. So we just get minus 36x minus 2x squared in parentheses. So let's take account. We'll have 1x squared, 4x squared, 1x squared, and this will be a minus 2x squared. So that's 7x squared. And then we have a minus 36x, 72x, and then plus 324 equals 9x squared minus 108x plus 324. So the 324s cancel out, and we just get like 2x squared equals 36x. Let's make sure we don't miss the solution. So I'll just write it 2x squared minus 36x is 0, and we factor. So we see x is either 0 or 18 in this case. So let's think about what each of these means, right? If x is 0, then the 2x, so let's draw our original triangle again. We have 2x, 18 minus 3x, 18 minus x. So if x is 0, this is a triangle of side length 0, 18, and 18. So it's degenerate. So then what parallelogram does it correspond? I mean, what trapezoid did it correspond to, right? So if we go back to the original diagram, this corresponds to a, let's add back the red parallelogram that I removed, right? So if we add this back, the sides were like 18 minus x, 18 minus 2. So basically, we'll see if x is 0, all sides are length 18, right? So we think, is this a trapezoid? Well, yes. If we look back at the problem statement, it just says AB is parallel to CD. And AB is a side of maximum length, so it doesn't have to be the unique side of maximum length. So yeah, sure, we could have all 4 sides be 18, and it'll be a rhombus, which is a trapezoid. If by trapezoid, we mean at least one pair of opposite sides has parallel sides. I mean, are parallel, right? At least one pair of opposite sides are parallel. So this satisfies the problem condition if, you check the problem statement. So, okay. So x could be 0. If x is 18, then what we have is, let's just do the original trapezoid. So this is if x was 0, if x is 18, let's cross that out. Then we get, well, clearly we'll just see, we'll have 18 minus x is 0. This will be negative 18, and this will be negative 36 for 18 minus 3x and so on. So yeah, this won't work. So x could be 0, x can't be 18. Interesting, it's kind of like we got some a degenerate triangle and an x value that gave negative side lengths. So maybe we try another orientation, because there are 3 factorial permutations of the ways we can assign 18 minus x and this to the 3 remaining side lengths of our trapezoid. So let's just go with the other one. So we'll have 18. We'll have 18 minus 3x this time. We'll have this and we'll have this. So again, we remove a, I don't know what the configuration looks like, but we remove this trapezoid, this parallelogram, where we, construct this point E such that, DE is parallel to CB, even though my diagram doesn't look like it. So, what do we get in this case, right? Well, we get another triangle. Here, because this is 18 minus 2x, this will be 2x, because the opposite side to CD will be BE, and this is also 18 minus 2x. And these two now add up to 18. So we get 2x, 18 minus x, 18 minus 3x. Now, the astute among you may recognize that maybe there is a shorter way we can do this, but let's just see how I first explored it, or something similar along those lines. So law of cosines gives us if we use it on angle A in the triangle. So now, let's just simplify. This was 2 times 1/2. We'll get this is, and this will be, so 9x squared plus 4x squared is 13x squared, 108x plus 324. And this equals this. So the 324s cancel again. We have a plus 6 here because there's a minus minus. So 19x squared. We have a minus 36x minus 108x. And then the 324s cancel, and this just equals like x squared minus 36x. So we'll get 18x is x squared is 108x. So here x is 0 or 6. We already did the x is 0 case, so what happens if x is 6, right? Well, if x is 6, then 2x becomes 12. 18 minus x is 12, and 18 minus 3x is 0. So our trapezoid has a leg of length 0. If we draw the original, I think it was like this. So what this tells us is like the bottom is 18. This is 12. This is 6, and this is 0. So really, it's just a degenerate quadrilateral and also a degenerate triangle, because you have a stick of length 18, a stick of length 12, and a stick of length 6, and it collapses to a degenerate triangle with side length 6, 12, and 18. So that's not a convex quadrilateral like the problem was saying. So we should ignore that case. But now that we've done this, something should really ring some alarm bells in us, right? We got degenerate triangles in or things that like had negative side lengths in like 2 of our cases. So how could we have seen that this was degenerate at the start, right? At the triangle step. So again, we had 2x, 18 minus 3x, and 18 minus 2x, no, x, after we remove the parallelogram. Does anyone see it? I'll give you a second. Here it looks like we have the degenerate case of the triangle inequality, right? Which says that A plus B equals C. So yeah, is that true for any 2 of the 3 sides here? Well, if we assume this is the largest side, then it is true that this side plus this side equals this side length, right? So it is true that we have the degenerate case of the triangle inequality. So this will collapse to a straight line segment. And the leg length will equal to 0. So the quadrilateral will be a degenerate quadrilateral once we add back in the parallelogram that we removed. So, okay, cool. So now, instead of checking all 6 cases, maybe we can eliminate some of the cases, right? So let's see which cases we can actually eliminate. And, maybe you saw this at the start. That's fine and great for you. I personally did not. I spent, at least 10 minutes trying 4 of the cases and finding that they all gave, kind of 0, lengths of length or side lengths of 0 and stuff. So, this is a more realistic solution presentation than just telling you that the triangle inequality is, in the degenerate case immediately, because you probably won't notice it immediately for, a lot of people trying it for the first time. So, what was I gonna do? Yeah, so we have 18. So we found that, if we had 18 minus 2x on top, then removing the parallelogram will give 2x, 18 minus x on one side, and 18 minus 3x on the other side. So in both cases, whether or not we swap these 2 side lengths, because we know one angle is 60, it's not symmetric, it's always true that this plus this equals this. So if we just assume that all the side lengths are non-negative or positive, then we can conclude that this must be the largest side. So the 2 smallest lengths add up to the largest side, and we can ignore these cases for the most part. If we look at the other case, let's say 18 minus x is on top. So one thing maybe we should also check is, what if 2x is the largest side, right? Then the triangle inequality would say 18 minus x plus 18 minus 3x is 36 minus 4x, and this should be greater than or equal to 2x. And there's not really any problems there necessarily. We can definitely find positive values of x that will make all 3 side lengths positive in length, and yeah. But also, if you really think about it, just having 2 sides algebraically add up to the algebraic value of the third side, will just it'll always mean that the third side is biggest or equal to the biggest, or tied for biggest if 2 of these 2 lengths are non-negative. So now let's just do the other cases. So 18 minus x, 18. We remove this parallelogram. This is 18 minus x, meaning this is just x. 18 minus 2x, 18 minus 2x, 18 minus 3x. So let's see. We have this triangle. Does this fail the triangle inequality? Well, we can see that this plus this, 18 minus 3x plus x, is equal to 18 minus 2x. So yeah, it does fail the triangle inequality. One thing that might be worth remarking on is, one degenerate case from earlier actually gave a valid case. So we should come back to that. So now we know that 18 minus x cannot be on the top, or else we'll have x plus 18 minus 3x equals 18 minus 2x. So the only possible value, whoa, not really sure what happened there. Let's see. So let's just continue. Okay, here we go. The only possible value for the side opposite the 18 length would just be this. And then we'll have 18 minus 2x and 18 minus x on one side or the other. So we should check both these cases. By the other case, I mean the 60 degrees is adjacent to 18 minus 2x. But 18 minus 3x is opposite the longest side. So at least we're done with the configuration issues part. So, okay, if we remove the parallelogram here, then what we get is the bottom is 3x. This is 18 minus x. This is 18 minus 2x. We can check the triangle inequality if we want. It seems like this plus this is greater than that, so there's no issues on that end. There could be triangle inequality issues with two of the other three sides, but we won't worry about that for now. We'll just solve the law of cosines equation for now. So it doesn't matter if I negate this since you know, a number squared is equal to its negative squared. So here we'll have so 3x times 18 is 54x minus 3x squared equals 36 times 2 is 72. So let's just clean this up a bit. We'll have negative 3x plus 10x. We'll have a negative 36x and a negative 54x. It's negative 90x. And the 18 squares will cancel on both sides. So this just equals 4x squared minus 72. So 9x squared minus 18x is 0. So it looks like we get either x is 2 or x is 0, right? We already found the x is 0 case from earlier. So the only new solution is x is 2. You know, if we want to do a sanity check, we might consider, you know, what was our triangle again? So 3x. Okay. So 3x. So if x is 2, this just becomes 6. What is that? 16 and 14. And this is 60 degrees. So, you know, you can kind of just check that this will work if you really want to. This is 6, this is 60, this is 3, this is 13, this is 3 root 3. We can check that 169 plus 27 is 14 squared. So that seems fine. These add up to 16. And there's no triangle inequality issues. The other case we should check is this one. So here we remove a parallelogram again. Again, we get 3x and 18 minus x, 3x that is. And yeah, it's just the same thing, but the sides are a bit swapped. So you know, you can probably do the law of cosines thing by yourself at this point. So I'll just remark that again, you get x can equal 0. And I believe last night I got x could also equal 5. So it became 15, 13, and 8. This satisfies the triangle inequality. And you can do a quick sanity check that you know, the sides kind of work out properly. If this is 15, this is 15 halves, this is 1 half, and this is 15 halves root 3, then using Pythagorean theorem on this triangle should give the correct value of 13 for the hypotenuse. So, we should go back to our first case and see what quadrilateral does it correspond to, right? So here we subtracted an 18 minus 3x, which is 12 from both sides when x is 2. So we should add back our parallelogram that we removed. So this was 16, 14, 14. This is 12. So here it looks like the three other side lengths are a equals 12, 14, and 16. And a could be any one of the other three sides according to the problem statement. We also had a equals 18 from the first case. Now let's check what happens in this case. So here this is 3 less than 18, so we need to add back 3. So this is 3, 18, 13, and what was that? 8? Yeah. So in this case, we get a equals 3, 8, 13. So if we sum up all the possible values of a, these three sum up to 3 times the middle, which is 42. That adds up to 18. This adds up to 60. And finally, these three sum up to the 3 times the middle. They're in arithmetic progression, so it's 3 times 8 is 24. 24 plus 60 is 84. So we get our final answer of 84, and we're done. You can go back and see if that's an answer choice, and in fact, it is. So, we went a kind of roundabout way of doing this because realistically, you might not see the triangle inequality way at the very start, which was definitely the case for me. I went through all 4 of the 6 degenerate cases before realizing that you can just ignore those with the triangle inequality observation. Another thing that I want to remark on is like which degenerate cases are okay, right? Because there was one degenerate case that actually gave a valid trapezoid, right? And that was the case when the bottom was 0. So if this is 0, if this is 0, and this is whatever it is, and this is whatever it is, then this actually gives a valid quadrilateral, right? Because you can add back the 18. So you get 0 plus 18 and 18. Well, I guess this should be 18 then. And this is a valid quadrilateral. So it's okay for it to be a degenerate triangle if the bottom is degenerate, because we need to add back a parallelogram which spans a positive bottom length or base length. And as long as the 2 sides of the triangle that correspond to the sides of the trapezoid are non-zero, then it actually gives a valid positive area quadrilateral. So this degenerate case where the bottom is 0 is okay. The other degenerate cases where one of the legs is 0 is not okay. In those cases, you'll get 18, a length 0, and then length like k and length 18 minus k. So this gives a degenerate quadrilateral and a degenerate triangle, because one length is 0 and the 2 smaller lengths add up to the largest length. Okay, so we have to be careful about that and not forget the 18, 18, 18, 18 case, which was a rhombus, which is a type of trapezoid. Another thing that I want to remark on is, some people might say, oh, instead of removing the parallelogram, you can remove the rectangle in the middle. So that turns out to be okay for the most part. And what I mean by removing the rectangle is, you can collapse this part. Like if this is 18 minus 2x, This is 18 minus 2x. And the two green lengths add up to 2x. K, 2x minus k. Sorry, let me write that a bit less thickly. So this is okay for some configurations of trapezoids, but if your trapezoid looks like this, which it could, maybe it doesn't in this problem, but in general, trapezoids can look like this. Then removing the rectangle by dropping altitudes doesn't work out as well because part of the rectangle is actually outside the base. The bottom base of the rectangle is outside the base of the trapezoid. So here it's more proper to say removing the parallelogram, since this way you'll never go outside the base. You might wonder, what if it was like this? Well, it said the bottom was 18, or the maximum side was AB was 18. So here this would be the maximum side, and we don't need to worry about that in our problem. So we don't need to worry about removing a trapezoid that is like, or a parallelogram that is like that. So those are just all the mathematical remarks. So let's kind of review, what were the key steps, right? The first step was recognizing that to attack a trapezoid problem, you can remove the rectangle. Remove a parallelogram to make it a triangle problem. I misspelled that, but it's okay. So as long as we remove a parallelogram along the shorter base, then it becomes a triangle problem with the green triangle. The second key step was to notice the triangle inequality. Failed in 4 of the 6 cases. So this is not an easy observation, and neither is removing the parallelogram observation. But if you can notice these both relatively quickly, then this becomes a more doable AMC number 12, number 24. Personally, it took me quite a while to remember this trick and also notice this. I tried all 4 of the failed cases with law of cosines first. So yeah, it took me at least 30 minutes to eventually come to a full understanding of this problem. But I think overall it's a reasonable number 24 for the AMC 12 because the triangle inequality failure was actually pretty nice, and so was moving the parallelogram. So yeah, that's it for this video. Hopefully I don't need to remake it, but if you have any questions, comments, concerns, let me know in the comments below. And I will post some other information about some of my other internet activity and online teaching program in the description below. So thanks for watching, and I will probably do an AMC 10 video next on a certain AMC 10 geometry question.